So if we start to roll through this piece here, we've got this idea of the 99 coming through this first piece, then getting into this piece of code, this else if points is less than 100, then it's going to be when equals false. So this first piece of the table will give us a false. So we'll fill this out here as false. If we come into here with the same A, we're going to work through all of these in A first, and then we'll go through the next line in B and C and D and E, just so we can work through one algorithm at a time. So with algorithm A, we've got 100 points here. So if points is greater than 100, then we've got when equals true. Well, it's equal to 100, so it's not going to fire that. And then it's not going to fire this either, else if points is less than 100, when equals false. So we don't know what this is going to be. It's going to be whatever when was set to previously, but that could be a question mark here. So we'll put into here this other statement, which would be a question mark of we don't know what it'll be. I'll just put a star here for that since it's not letting me do anything over there. All right. Let's actually move this down here. All right. Question mark. Okay. So that will be the unknown question mark where we have 100 points here. Then if we go in here with 101 points, this is greater than 100, when equals true, and we kick out of here. So we've got this other condition where we've got the 101, so we're going to have a true in this one. So when will be true in this particular case. All right. So we see already that algorithm A has some problems with the equal to 100 points portion here. So let's go ahead and go into the next algorithm, algorithm B. If points is greater than 100. So if we start at this 99 again, then we're going to bypass this points is greater than 100. Else if points is less than or equal to 100, we have when equals false. So over here, when is going to be equal to false because we've got this less than condition here. So this one's going to give us this condition. And we'll move this false over to here. So the next piece we want here is points equal to 100. So in this case, we're going to bypass this if. We're going to come into this else if, and we're going to, at this point, have a false. And this time we will get the false that we're looking for because we've got an less than or equal to for that 100. So this is actually going to come out correctly. Points greater than 100. It's going to actually come out true. So this one will give us another true over here. So looking at algorithm C, we've got points equal 99. If points is greater than 100, when equals true, else when equals false. So we're going to go here and we're going to get when equals false. This one. Then we're also going to get when equals false for this 100 too, because it's less than 100 and it's not greater than 100. All right. Then if we've got this 101, we've got points when equals true. So this answer false, false, true in this case as well. Algorithm D, if we look at this, 99 is going to give us here the less than 100, which is false. So we're going to get that correct answer of false. And we're going to come to 100 here, and this one's also going to have problems with the 100 because we're going to get points greater than 100, and then if points is less than 100, we're going to have false. We're not going to hit either of those conditions, so we're going to hit the question mark again. And it's going to be set again to whatever win was set to begin with, whatever we initialized win to. So that could be correct, could be wrong. So we'll have to see what that would be. So then we come over here to the last one here, which is 101. And we're going to get this points is greater than 100. So we're going to have win equals true. And that will come out of here. So we're going to have, again, missing cases here for this 100 here in D. So D is going to be another problematic algorithm. So then if we come into E, which is our final one, win equals points greater than 100. So in here is 99 greater than 100. No, that is false. So win is going to be false. We've got this particular case here. We've got points equal to 100. 100 is not greater than 100. It's equal to, so that's going to be false as well. That's the correct answer. And then win at 101 points, it's going to be greater than 100. So we're going to get this final one to be true. So that's how this table folds out. So as we look at it, we've got three solutions that can work. We've got B, C, and E that are all going to give us correct answers or our correct algorithmic solutions to this particular problem. So because we just stated up here, we wanted it the players win when their score exceeds 100 points. So these are the three that work, B, C, and E. Of these three, you can see that E is the most compact. This is probably what we would call the most elegant solution here, because you're actually, depending on this particular clause here, this evaluating this Boolean statement of points greater than 100. And this is a valid statement and will give us valid answers here. So this is going to give us the correct answers across all of the cases. Same with these two, but these two would be a little bit more code. This one over here has the else if condition, so it's going to be a little tighter. Doesn't need it in this case, because if you write it correctly, these are the same algorithms in B and C. And I think C is easier to understand. So we would probably prefer C because it's going to be easier to understand. If it's greater than 100, it's true, else win equals false. But you can condense this even more into this win equals points greater than 100. And if you look at here, the points greater than 100 is the same conditional that we're using through all of these to start with. So, all right. Given that one, got those pieces. So how does that relate to recursion? Well, recursion is the idea of calling a method calling itself. So it starts to get into this really inception kind of thinking, where you're calling a method that you haven't fully defined yet to get the answer to the next one down, quote unquote. That's how I like to think about recursion, is you're looking at the next one down, because usually you're counting down to 0 or some known numbers. And we'll see in the homework that those known numbers may not be 0, they may be other numbers in a series or a sequence, and they may be defined in particular ways as we look at some of the series and how they're defined in that mathematical functions homework. But we'll get to that in a little bit. So one of the classic recursion examples is the idea of factorial. Addition of a factorial, so this exclamation point, 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. So if you take 5 and multiply it by every other number below 5, you should get this 120. So that's the idea of and the definition of factorial. If you have not run across that in math prior, hopefully you have. Most math classes would have covered that at some point between fifth grade and now, you should have seen the factorial. I think probably in high school algebra 2 or maybe trigonometry might have covered that. So this idea of factorial is the number times all of the numbers down to 0 before that number. So if we calculate 4 factorial, that is 4 times 3 times 2 times 1. So that's the way we want to think about that as far as how to write out that expression, or we can write it out as 4 times 3 factorial, and that would be the same thing. So if we write that out, we can write that out as 4 times 3 factorial, and then we would find 3 factorial writing out as 3 equals 3 times 2 factorial, 2 equals 2 times 1 factorial, and that would be 1. So we've just 2 times 1, so that's 2. And we've got 100 factorial equals 99, 100 times 99 factorial, and then so on and so forth. So n equals n times n minus 1 factorial. That's how you would write this as far as the basic algorithm for this. All right, so we keep breaking these problems down into smaller and smaller problems until we get to a case where we've got one that is able to be solved. For example, in a problem 0 factorial is referred to as the base case. So 0 factorial is 1. And so that's, as we're looking at these things here, 0 factorial is this base case, or the last thing that happens. So the algorithm for factorial is this one here, where we want to take the factorial of a given integer n, so in this case maybe 5, then we're going to come out here and we're going to, in this case, we're printing out some interim results so we can kind of get some ideas of what is going on beforehand here. So we've got this idea of factorial, and the idea of items below that. Go turn my notifications off here so that I can stop receiving some stuff. Put it into do not disturb, hopefully. Maybe I can't. All right, let's just get back in. So here we're printing this print. We don't have to do that to solve the problem, but we're going to do that here as kind of a diagnostic to see what's going on. So if I come out to here, I've previously loaded a item here for the Java tutor. This Java tutor here will kind of go through this. So we're going to start off in main, and we're going to print out factorial. We'll step through this. So if we're printing out this factorial, this is spelled wrong, so I have to go back and edit a piece of code. So we're coming into here, and then factorial of 3. So here is the memory stack diagram for that. So we're taking this factorial of 3, n equals 3, and we're coming into line 4 over here. That's what this is showing here. And we're going to say n is 3. And as we walk through it, if n equals 0, return 1. So that is what we call the base case and is labeled as such. So when you're doing recursive code, it would be really good if you're doing comments to label your base case. That is the case that resolves at the final call of the chain for the recursive call. So we're not at that base case yet. We're looking at n equals 3, so we're going to hit the else statement here, and we're going to say we need the factorial of 2. So answer equals factorial sub 2. So that's going to be the call that we make here. And that spawns another call here to factorial of 2. And that means we're going to come back into here. N is 2. And then we're going to see this come down to here. N is not equal to 0, so we're going to go to the else, and we need the factorial of 1 here, because we need the factorial for n minus 1. That's what we're doing here, and that's what we're showing here, n minus 1. We're going to go into here and call factorials of 1, and we're going to go n is 1. I'll print that out in a moment here. Go ahead and pull this down a little to get more room. So n is 1. We're going to say, is n equal to 0? No. And then we're going to hit this else and come into that statement there. And we're going to need the factorial of 0. So now we're going to call factorial of 0. And we're going to say n is 0. Print that out. Then we're finally going to hit this base case of n is equal to 0. So we're going to return a 1. Then what happens is some magic, as it's referred to in programming ease. And this is where this 1 gets returned. Then the return of the one above it can be calculated, and the return of the other one, so on and so forth, all the way up to 3. So we get factorial of 1, and then these things start to change over here, as we can see. So our answer is 1. Then our answer and return value becomes 1. We're going to come back to here and get our factorial of 1 is 1. And the factorial of 2 is 2. Then the factorial of 3 is 6. As we come out to here and we're multiplying 3 times 2 times 1 times 1. So that is 3 times 2, 6 times 1 is still 6. So that's how this factorial works as you walk through it. So remember, you can always come out to this Java tutor and kind of walk through these pieces. This will give you a good idea of what the memory stack diagram would look like at any given point. So if I asked for the memory stack diagram for a recursive call, which I don't think I will do at any point, but this would be how you would do that. If I asked for the recursive call at line 8 through the second call, this is what that would look like. So this is the memory stack diagram that would return. So make sure you understand how to trace and what the memory stack diagram is looking like at any of those given points. And then I'll go ahead and put this to the side. We'll get into, again, line 7 over here is your don't think that's the correct line 7 over here. So let's go back to line 7 over here. Line 7 over here is the factorial call. So this is the factorial sub n minus 1. That's the answer here. Why is the if statement required on line 3? And line 3 over here, that is the base case trigger here. So that is the reason we have this n equals 0. And if n is equal to 0, then we have the return of 1, or the base case over here. So make sure you know how to identify the base case, and then the recursive call, which line 7 would be the recursive call. All that. So then you want to understand how many calls are being made in here, and what happens if we try to calculate the factorial of a negative number. In this particular one, we would blow up, because we're not going to be able to get to 0, and it would just keep going out to infinity. So what we want to do is, if n is great over here, you'd want to make sure that you're not, if n is greater, want to return 0 or something invalid. So you'd also want some kind of other statement in there to make sure that you've got a protection against this bug for negative numbers. So that's that piece there. From here, I'm going to go ahead and get into the homework here. So let's take a look at that over here. Homework 8.1 is the math functions. We've got this idea of three different functions here. One is exponentiation, x to the nth power. And again, here you can assume that n will not be negative. So that's what we're going to do in here. So what we want to do is make sure we have cases understood here for all of these cases. We've got this binomial coefficient here too, which is assuming n and k will not be negative. So these are the assumptions that we're making. You can go ahead and make those in any code that you're writing. Then we have this third one here, which is this Ackermann function, and it has three definitions here. So we've got three pieces in here. Each of these should be less than 10 lines of code, so don't overthink these. If you get stuck, please ask on Piazza and check. Again, these should not be more than about 10 lines of code each, so make sure you are working through these in a way that you understand that. So don't spend too much time on either of these last two before you ask questions. Especially in recursive methods, you're going to find that either you're getting it or you do not. And if you do not, you really need to get to the point where you're understanding what this recursive call is trying to do. First of all, you should try and go understand the math behind these. So you may need to go visit these Wikipedia pages and kind of understand what the math is that's being asked for here, and go through these functions and understand the mathematical resolution. So plug in a couple small numbers and do these on paper. Again, I can't emphasize enough doing this on paper to understand what the math is trying to do before you actually try and go code what the code is supposed to do for these two, especially these two here. Exponentiation, I think most of us understand that pretty well, but this binomial coefficient and then this Ackermann function are a little bit more abstract, especially the Ackermann. It's a fairly recent discovery even. So make sure you understand how those will work, and then package those into a mathfunctions.java. Again, I'm going to go over this in a little bit to give you a starter code for some of these, and then have you finish that out. But just wanted to kind of outline these right now. So the simple counts here, exercise 8.2, we're going to go back to Coding Bat, and you should be able to do most of these on Coding Bat for a bit of them. So you'll see this Recursion 1 piece over here that you'll have some items for. And we're going to do the particular one, bunny ears, over here. And so we want to come into here and figure out what to do with this bunny ears. We have a number of bunnies, and each bunny has two floppy ears. We want to compute the total number of ears across the bunnies recursively. So we'd want to come into there and kind of figure out what we need to do to get to that resolution. And I'm going to go ahead and show you this particular solution here. I'll log into my previously finalized one. So in here, we've got this particular solution here for bunny ears, where we've got the base case. If the bunny is equal to 0, just return 0. So that's the base case. We don't need to do anything more for that than just return 0. So we've got this: if bunnies is equal to 0, we want to return 0. And in this case, for our benefit of getting this to pass check style, we would do this to wrap that into a so we want to do that. Otherwise, we want the recursive case, and the recursive case is going to call for us to make a recursive call with bunnies -1 that will get us towards that base case and fix what it returns. So over here, we return 2 plus bunny ears sub bunnies -1. And the reason we're doing that is each bunny has 2 ears. So we're going to take the 2, and then we're going to add to it the number of bunnies that remain here. So if we've got bunny ears sub 2, we're going to return 2 plus bunny ears sub 1. And then we got to calculate that. And bunny ears sub 1 is 2 plus bunny ears sub 0, which is going to give 0 back here as the return case here. We've got that 0 over here. So we've got that piece that we're rolling into, and then it rolls up from the 0 to the 1. 2 plus 1 is 3. So or 2 plus 2 is 4. So that's what we're going to get as 4, because we've got bunny ear sub 1 is 2, and then bunny ear sub 2 is 2. That's going to equal 4 altogether for bunny ear sub 2. So if we run these things, we can see we've got all the different cases that it's going to go ahead and pass. And that's the solution for the bunny ears particular problem. And I'm going to make available a couple of these files out here. Let me go ahead and do that right now so that you can follow along with that. It's under, again, under code in here, and publish, come on, take. So publish homework 8. This is going to have our different items here. I'm also including the stars.java, which is the starter for the lab for today as well. I'm not going to collect that lab. Again, I'm trying not to make too much do. And also we have an exam this week, so everything got compressed a little bit. So I don't want to have you overloaded with homework or work to do that is turned in. So I'm not going to collect that lab, but it is a really good lab to study for the exam with, because it is asking you to do a lot with loops and for loops. So I'll go over some of that towards the end of class here, but I just wanted to make sure you did not have too much work to do. Again, 8.1 through 8.3 are what are due for homework 8. Homework 9, we'll probably get back to all of the homework being due, because that will be due the following week, and that'll be after the exam. So you'll have a little bit more time, hopefully, to get into that on Thursday and beyond. And we'll go over some of that on Thursday next week after the exam on Tuesday. So exams coming up are Thursday. We'll have the written portion in Canvas. We'll take that live here. I would like to have all webcams on for that. So if you need to play with webcam settings, etc., I will probably have some things open here for an open meeting. I'll probably try and set up another test meeting tomorrow morning sometime, just to have you be able to make sure your webcam is working. It's one of the only ways we can kind of know that it's actually you out there in the internet land taking the exam. So I'd like to make sure that you have that capability. So while you're taking the exam, also you could ask some questions, raise your hand, ask questions about the exam too. So that's why we're doing that as a live kind of WebEx, and then giving you the code to enter the exam on Thursday. That's how that will work. All right, so let's get back to this bunny ears here. Then we're going to go ahead and take this bunny ears problem, and we will go ahead and add that over to our simplecounts.java. Again, I've started that for you over here in Canvas. So that should have this bunny ears, and then I've given you 2 stubs in here for the triangle and the sum digits here. And then there's a main method here. You can use the main method to test some of these things and make sure things are actually returning what they should be. With a triangle and some digits, those actually are available again on Coding Bat, so you should be able to get these tested offline without having to submit to AutoLab. That's kind of one of the other things I'm going to try and do, is provide a lot of offline tests so you don't have to burn submissions or also connect to the VPN to submit to AutoLab. So this code is available on Canvas. already. Next one we're going to look at here is this running totals. So running totals is going back again to the some more of these cases for coding bat. I'm going to go take a look at this particular one. So in this particular one, count 7, we're given a non-negative int n, and we want to return the count of the occurrences of 7 as a digit. For example, if we have 717, it's going to yield 2. We're not going to use any loops, and note that mod, the percent operator, by 10 yields the rightmost digit. So 126 mod 10 is 6, while divide by, or integer division by 10, removes the rightmost digit. So 126 divided by 10 is 12. So in this case, how we're going to do this is we're going to do a combination of mod and div, or division by, or integer division, to get the recursive call accomplished. So we're going to set up a count here, and count is going to equal to 0. Then the base case here is going to be if n that we're passing in, this parameter n, which is an integer, if n is equal to 0, then we're going to return 0 because there are no occurrences of 7 in 0. So that's the final base case that's going to kick us back up the chain. Otherwise, if n mod 10 is equal to 7, we want to set count equal to 1 because we have a 7 in that tens digit place. So in the case of 717, if we do n mod 10 is equal to 7, which it is in that case, then we return 1 for the count. Our recursive call here is that we're going to return count, which is 0 to start with, plus count 7 sub n divided by 10. So that would be, in this case, we're going to get 1 returned here plus count sub 7 of 71. And then we're going to go in and do the 71. We're going to come into here. We're going to say, is this n mod 10 equal to 7? In the case of 71, no, it's 1. So we're going to not count. Then we're going to do count. So count is 0. So it's 1 plus 0 right now. And we're getting that to be 1. Then we're going to go count 7 of 7. Because it's n divided by 10, which if we were on 71 and we're integer dividing that by 10, we're going to get to the 7. So we're going to come in here with 7. We're going to count equal to 0. And if n is equal to 0, which it's not, then we're going to come into here. If n mod 10 is equal to 7, which it is, count equals 1. We get a return of 1. So this will be 1 plus 1. It'll give us that 2. And the last piece we're going to do is go ahead and go into that 7 mod or 7 div 10, or divided by integer divided by 10, and that's going to give us a 0. So we're going to come into here, count is equal to 0, n is equal to 0, we return the 0 and go back up the chain, and we have our return of 1 plus 1, which will give us 2 as the count of that. The rest of these that are in this particular set, count 8 works very similar to count 7. So hopefully you should be able to figure that one out without too much trouble. Bunny ears 2 is just another redo of that one. So I'll let you guys figure that piece out. And the starter code for that, as well as some tests, are in Canvas here. So that is the running totals, I think. Let's go back here to, yes, running totals. So running totals looks like this. This is going to give us some running totals. I've given you count 7 here, so you can get that. Just went over. Count 8 stub and bunny ears stub is included here as well. So those are some starter files for you in there. And I've also given you this math functions test.java. These are some test files or test assertions for a math functions.java you can go ahead and run these tests, associate these tests in JGrasp to get this to run, and then test all of your solutions with these tests. When you pass all these tests, then you should be able to submit to AutoLab and get a 10 out of 10 on that piece. So these tests can be downloaded. Again, they're available here, mathfunctionstest.java. So you don't have to do any testing online in AutoLab except for your final tests. And you should be able to do your check style as well offline before actually submitting that to AutoLab. All right. So those are the 3 homework problems that we're going to be doing for this time out. I'm going to go ahead and go into one last thing here, and then I'll basically turn that over to you if you've got any questions on doing these, or if you want to get started and take a look at some of these things. I'll be around for some office hours after that. So what I wanted to go into was this lab 15. If we go down to here and go to current week, lab 15. This will take us into the stars lab. So we want to download this stars.java file, and we're going to want to print these patterns out. So if we have a number that we're passing over into this pattern, we're going to want to have the pattern reproduce that number of stars all the way down to 1 star at the end. So I'm going to go ahead and download this stars.java. I already have over here. Let's go grab stars.java. Grab stars.java. Let's open it with JGrasp. Hopefully this time it'll actually open, unlike on the computers at campus. All right, yes. Close out these 2 files, and I'll go ahead and go into the stars.java over here. And it's got a bunch of starter code in here. I've got some starter here that I've added for you. Max row count, star count, blank count. These are variables that we'll be using to enter things in. It's going to ask you to enter a positive integer for the number of rows. Then you're going to enter something like 4. In running this, I'm going to go ahead and compile it. If I run it, I'm going to enter in 5, and it's going to give me these different patterns here. So pattern, first example would be increasing number of stars. So that one's given for you. We wrote that already. That's just this example. First example here, basically you're taking a for loop here. We're starting with row 1, and then we're going up to the 5 that we entered as max rows. Then we're going to have a star count equals the row, and that's going to be the same thing. And we're going to come in here and loop through each row to make sure we're going to the end of that row, how many items we have. Then we're over here increasing the row count in that outer loop. So this is all about nested loops. You're going to have an outer loop that is your column count, and your interior one, which is your row count, which actually, or sorry, your row count will be the outer one, your interior one will be the column count. So how many columns are you printing in this particular one? So in this case, we start off with 1 star, then we're going to go to 2 stars, 3, 4, 5, and then we quit. The next example in pattern A is kind of the reverse, or the flip of that. We're going to start out with 5, and we're going to go down to the 1. So you can see how that is accomplished. And then pattern B basically is going to be a reverse of that. So instead of thinking about the stars, we're going to actually think about the spaces, and we're going to need to use these or blanks, and we're going to have this blank count that we're going to use through this piece. So this is a really good exercise in trying to prepare for the coding exam for exam 2 that will be next Tuesday. So I highly recommend you go through the C and the and then if you're really up for a challenge, there's that last one that is, I think, the pattern E or D here. So if you want to figure out pattern C, I would actually roll through this and make sure you understand how pattern A and B are working, even though I've given you the code. Again, you should probably try and come up with your own version of that, and then definitely try and come up with pattern C to finish that out. And if you want extra practice, you can go and do this pattern D. This is even more complex. It only works with odd number of rows, because you're going to need to have something where you can have this one in the middle of the diamond. So that's it for class material that I was hoping to cover, and I'm going to leave it open for any questions that you guys have. You can either put that into the chat, or you can audio that up. So as far as I'm concerned, this is what I was hoping to cover for class. I'll go ahead and stop the recording now, and I'll make this one available later.